All right, let's dive into something that seems so simple, but gets surprisingly deep.
Sounds intriguing. What are we tackling today?
Well, have you ever stared into a fire?
Who hasn't?
You see that mesmerizing glow, those dancing flames? What's actually happening there scientifically? Why do hot things like those burning logs emit light?
Ah, you're talking about blackbody radiation.
Hmm.
It's this fundamental concept in physics where an idealized object, a blackbody, absorbs all light, reflects nothing back.
Like a perfect light sponge.
Exactly. And by studying what kind of light it does emit at different temperatures, physicists hope to unlock some core secrets about how light and matter interact.
So it's a simplified model to study something much bigger.
Precisely. But here's where things took a turn for the catastrophic. Their calculations, based on classical physics, led to this prediction called the ultraviolet catastrophe.
Okay, that sounds dramatic, like exploding oven-level dramatic.
Pretty much. Imagine expecting a gentle warmth, but instead, your oven unleashes the energy of 1,000 suns.
Yeah, that's not how my toaster oven works. Clearly, something was off with their assumptions.
The issue was how they viewed energy itself. They treated it like a continuous stream, like pouring water from a pitcher, any amount, big or small.
So not like a smooth, flowing river of power.
Not quite. Enter Max Planck in 1900. He drops this bombshell. Energy isn't continuous, it's quantized. Imagine ice cube trays instead of that pitcher.
So instead of any amount, energy comes in those specific ice cube-sized chunks.
Oh, got it. He called these packets quanta, and it revolutionized physics.
Okay, but how does this save us from the exploding ovens and tie back to the glowing objects?
It all boils down to how atoms, those tiny building blocks of everything, interact with light. You see, inside each atom, you've got these electrons, right?
Right, those tiny particles zipping around the nucleus.
And these electrons, they can absorb and release energy.
Like tiny little energy sponges.
Kind of. But here's the catch. They can only handle those specific, quantized amounts Planck talked about.
Ah, so it's more like a vending machine. You can only put in certain coins, get specific snacks.
Exactly. Think of it like a staircase. Electrons can only exist on those steps, those specific energy levels, not in between.
So no sliding down the banister for these electrons, huh? It's all about those precise jumps.
Precisely. Now, when an atom absorbs energy, say from heat, an electron can jump up a step or two on that staircase.
Gets excited, right? Like us before a deep dive.
You got it. But they can't stay excited forever. Eventually, they want to jump back down to their chill, ground-level state.
Okay, so what happens when they make that jump back down? Do they just disappear for a second?
Not quite. When an electron drops down to a lower energy level, it releases that energy difference. And guess what that release looks like?
Let me guess. Light.
Bingo. It releases a photon, a tiny packet of light energy.
So the color we see, that depends on how far the electron falls down the energy staircase.
You're catching on. Each color of light matches a specific amount of energy. A big drop, lots of energy, that's your blues and violets. A small drop, less energy, you get reds and oranges.
Like a cosmic rainbow, all based on these electron leaps. But how does this explain those glowing objects we started with?
Think about it, when you heat something up, you're giving those atoms more energy, right?
Right, things get hotter, they vibrate faster, all that jazz.
Exactly. And that energy gets those electrons all riled up, jumping up those energy levels. As they inevitably fall back down, they release those photons, and that's the glow we see.
So every time I see something glowing, like a fire or a light bulb, I'm really seeing a massive light show of electrons jumping up and down these energy staircases. That's way cooler than I ever imagined.
It's pretty amazing. And here's the kicker, because energy is absorbed and released in these specific packets, thanks to Planck's discovery, there's no ultraviolet catastrophe. Those black bodies emit a predictable spectrum of light, not an infinite blast of energy.
So we're safe from exploding ovens, all thanks to quantized energy. That's a relief. But this all seems pretty theoretical. Does this actually matter for those of us who aren't physicists?
Oh, it matters a lot more than you might think. This isn't just some esoteric physics problem. It's the foundation for so much of modern technology.
Okay, now you're speaking my language. Give me the real-world connection here. What difference does it make in our lives?
Yeah, for starters, pretty much all modern electronics rely on understanding this quantum behavior of electrons.
Wait, really? Like my phone, my laptop, all that?
Yep. Computers, smartphones, even medical imaging like MRIs, they all operate based on those energy levels and quantum leaps we've been talking about.
You're telling me my phone is basically a tiny quantum physics lab. My mind is officially blown. But you also mentioned lasers earlier. How do they fit into all of this?
Lasers are a great example. They work because of this principle called stimulated emission. Basically, you can get a bunch of electrons to all release photons of the same energy and therefore the same color at the same time.
So instead of a jumbled mess of light, you get a concentrated beam of a single color. That's pretty incredible.
It is. And none of it would be possible without understanding how energy is quantized within an atom. It's like a cosmic symphony, with electrons playing the notes and lasers conducting the orchestra.
It's mind-blowing to think that this seemingly abstract concept of quantized energy has had such a concrete impact on the technology we use every day. It makes you appreciate the power of scientific discovery, doesn't it?
Absolutely. And this is just the tip of the iceberg. Planck's discovery opened up entirely new avenues of research and led to breakthroughs in fields ranging from astrophysics to material science.
It sounds like we could do a whole other deep dive on just the implications of Planck's work, and we probably will someday.
We could, but for now, I think it's important to zoom out and appreciate the bigger picture here. It's like we zoomed in on this tiny detail, the color of something hot, and ended up with this whole new understanding of how energy works.
And it's not just about fixing some equation, right? It literally changed how we see reality.
Exactly. Think about trying to understand the universe, but you can only use one hand.
Okay, that's a weird image, but I think I get it.
That was classical physics before Planck.
Yeah.
Powerful, but limited. His discovery was like suddenly being able to use both hands, grasp the universe in a whole new way.
And that new way is the quantum world, right? It
Yeah.
still feels kind of mysterious, like we're just dipping our toes in.
Oh, it's definitely a weird place. Forget those neat, predictable laws we're used to. It's all about probabilities and uncertainties.
Right.
But here's the thing. That quantum weirdness, those tiny energy packets, they're not just some small detail.
Don't leave me hanging. What else did they impact?
They have huge implications for understanding the entire universe, even the biggest stuff out there.
Okay, now you have to explain this connection. How do we go from tiny energy packets to the vastness of space?
All right, remember those glowing objects we started with?
Mm-hmm.
We now know that light comes from electrons jumping between energy levels in atoms, right?
Yeah, like a cosmic light show.
Now think about stars. Giant hot balls of gas.
You're not saying that starlight, the light from the sun, that's also these quantum jumps happening.
Exactly. Stars are basically giant blackbody radiators. The light they emit, it all comes down to electrons absorbing and releasing those specific energy packets. Planck's discovery is crucial for understanding how stars shine, how they create the elements that make up, well, everything.
So we wouldn't even be able to fully appreciate the stars without understanding this quantum world.
Nope. It's all connected, from the smallest atom to the largest star, all governed by the same quantum rules.
That's incredible. It really shows how exploring even the seemingly simplest questions can lead to the most profound discoveries.
Exactly. And that's what makes science so amazing. Every answer often leads to even more fascinating questions, driving us to explore further and deeper.
Well, listeners, I hope this deep dive has inspired you to look at the world around you with a fresh sense of wonder. The next time you see something glowing, whether it's a bonfire, a light bulb, or even the stars in the night sky, remember the incredible quantum dance happening at the atomic level. It's a reminder that the universe is full of surprises, and that the more we learn, the more we realize how much more there is to discover. Thanks for joining us on this journey into the quantum realm.